Hello everybody, Radu here from Infinet Wireless. Thank you very much for joining today's webinar. This time around we will discuss about the design of point-to-multipoint systems and more specifically about how you can implement frequency reuse and GPS synchronization within our Infinet Wireless PtMP networks. As always, we will have a Q&A session in the end, but if you have any questions during the webinar, please write them down in the chat section. My colleague Bogdan will also be online and he can answer some of your questions as well. So let's get started. The agenda for today includes 4 items. First, we will look at the main base station sectorization options, highlighting the advantages and disadvantages in each case. Then we will talk about frequency reuse. As we all know, there are many situations when you don't have enough available spectrum to assign different channels to all your base stations. So I will show you how you can reassign the same channel on multiple units and how you can avoid mutual interference between co-located devices. The third item will be about our GPS synchronization module called aux-audio sync. We will go through the main specifications of the device and I will show you how to connect it to the Infinet Wireless radios and how to configure it in order to make sure that your sectors are operating in perfect sync. And in the last item, we will look at some troubleshooting techniques that will help you solve some of the issues that might appear when you implement TDMA and frequency reuse within your PtMP networks. To begin, let's imagine that you have a certain area over which several subscribers are equally distributed, and these subscribers must be wirelessly connected to a central point. To do this, obviously you have to provide radio coverage for the whole area, and the problem can be solved in several ways, as you will see in a few moments. For clarity, first let's define some additional conditions for the problem. Let's say that we have 10 subscribers. The gain of the subscriber device antennas is 23 dBi, and all customers must achieve maximum modulation and an availability of 4 nines. Our solutions for this task are as follows. The first option is to install a single base station sector with an omnidirectional antenna. It will be cheap. You will only need one frequency channel, but the capacity of this sector will be split among all 10 subscribers. So you will only have 240 megabits per second for all customers. Also, the delay parameter will be a multiple of the total number of subscribers. In this case, if you use the maximum frame length of 10 milliseconds, then the packet delay for each subscriber will be at least 100 milliseconds. And the range of this sector will be no more than 3 kilometers. The next solution requires installing 4 sectors with 90 degrees antennas. This setup is the most popular choice for most situations because it strikes a good balance between capacity, range and delay on one hand versus costs and frequency channel requirements on the other hand. So the total capacity in this case is almost 1 gigabit per second. The delay will be about 25 milliseconds for each subscriber and the radius of good coverage will be almost 5 kilometers. However, 4 different frequency channels will be required plus an additional 3 as guard. And of course, 4 radio devices are needed here, not just one as in the first case, so the costs of this solution will be higher. The third solution, which is sometimes preferred by some of our customers, relies on using 6 sectors, each with a 60-degree antenna. This option is slightly more expensive than the previous one. And when we asked our partners what was the reason for choosing this solution, their main argument was to increase the coverage radius of the sectors. However, the maximum distance doesn't actually increase that much, only by a few hundred meters. Also, the total delay does not decrease by a huge amount as well. However, there is a key benefit here, and that is the capacity, which increases to almost 1.5 gigabits per second. But in return, you will need 6 different frequencies plus 5 channels as guard. Additionally, there is the 3-sector option as well, but it is rarely used, and in that case you cannot implement frequency reuse because all sectors are adjacent, so we decided not to include it in this presentation. So, as I explained earlier, the most common and cost-effective solution is the 4-sector configuration with 4 base stations per site. In this case, the recommendation is to use a different channel for each sector, and also another important factor that you shouldn't forget about when designing a multi-sector site is the guard interval. because most probably the base stations will be installed close to each other on the same mast. The influence of an adjacent sector operating using a neighbor channel is not as great as if the sectors would work on the same frequency, but some interference will be present and the overall throughput will be reduced. Therefore, the operating channels need to be spaced apart from each other. We recommend that the guard interval should be at least equal to the channel width. This means that if you deploy 4 20 MHz sectors, the total spectrum that you must have available is 140 MHz, as you can see in this picture. But as we know, there are situations when you don't have that much spectrum at your disposal. In case of licensed bands, spectrum might be limited or very expensive. In case of unlicensed bands, most channels may be heavily interfered by other devices operating in the area. So in these situations, you might be forced to use less channels than what is usually recommended, and you will have to deal with a lot of mutual interference between your sectors. Let's look at an example. The figure shows a 4-sector site with the back-to-back sectors operating on the same channel, so only 2 frequencies are used, F1 and F2. At some point during operation, base station 1 is receiving data while all of its neighbors are sending data to their subscribers. Since base station 1 and base station 3 are using the same frequency, BS1 will be heavily interfered by BS3 because the signal of BS3 will be more powerful than the one coming from the subscribers, so the reception will be affected. The same thing happens when BS4 is transmitting and BS2 is receiving. Even if the other 2 sectors are receiving this time, the reception at BS2 will be affected because BS4 is transmitting on the same frequency. So basically the issue is that at certain points in time, some of the sectors are transmitting and others are receiving data from their subscribers. Fortunately, there is a solution to this problem, and it involves deploying 2 key elements. First, the TDMA-based firmware must be installed on all Infinet units. TDMA is a medium access method that relies on fixed time slots for each subscriber. The TDMA firmware for the Infinet radio devices can be downloaded from our FTP server by following the link that you can see on the screen. And the second element is our external GPS synchronization module called aux audio sync. As you can see in the picture, when TDMA and the GPS module are deployed, the sectors are in perfect sync. All base stations send and receive data at the same time. So first, during the transmission period, the base station sectors do not affect each other because each subscriber hears the signal of the opposite sector much worse than the signal of its own base station, if he hears it at all. Accordingly, during the receiving period, none of the base stations will transmit anything, so the reception will not be affected by the powerful mutual interference. When we compare the spectrum requirements for polling and unsynchronized TDMA with the ones for TDMA with the synchronization hub, we see that in the second case, only 2 frequency channels are required. So instead of 140 MHz, only 45 MHz are needed by implementing the so-called ABAB system. Now, what about the guard interval in case of synchronization? Why is there only a 5 MHz guard? Well, the guard interval is proportional to the strength of the interference. When the source of interference is close, its signal becomes more powerful than the useful signal, like in the first case when we had no synchronization. Therefore, a large guard interval of 20 MHz was required. In the second case, the subscribers of neighboring sectors become the sources of interference. During the receiving period, a base station can hear, besides its own CPEs, other subscribers from the neighbor sectors through the side lobe of the antenna. However, the power of the interference is much lower because the unwanted signal is received through the side lobes. Therefore, we can reduce the guard interval. In general, we recommend using a guard of 5 MHz in case of synchronized TDMA. The ABAB system can also be adapted for situations when you use automatic frequency allocation or the regular DFS. Infinet units allow you to shrink the spectrum that is scanned for available channels by editing the frequency grid. In the example that you can see in the picture, for the 20 MHz band, the unit is only allowed to use frequencies between 4920 and 5000 MHz with a 20 MHz step. The frequency grid reduction is usually done either because not all supported frequencies are allowed for use in certain regions, or to reduce the scan time when a new channel must be selected. A narrower grid means less downtime in case of radar detection. As long as TDMA and sync are used, the same frequency ranges can be assigned for back-to-back sectors. The picture shows an example of a 4-sector site which uses two ranges of 80 MHz with 5 MHz guard between them, so 4 20 MHz channel for each pair of back-to-back sectors. And another special case that I want to show you is when you can use the same frequency for all 4 sectors. But please note that this is an extreme situation. We usually do not recommend using this setup unless it is the only option. So when you have a lot of Infinet units in your network and a really low number of usable channels, only 3.5 MHz channels in this example, obviously you will have a lot of interference between your devices. To reduce the interference, you can configure the units as SISO by disabling one of the transmission chains of each unit. The adjacent sectors should have different polarizations, while the back-to-back sectors will have the same polarization. This way you can spare one frequency channel and use it on the neighbor sites to reduce the overall interference levels. Obviously, TDMA and GPS synchronization must be used in this case. The separation between adjacent sectors is ensured by using the different polarizations, and of course the throughput will be much lower if you use SISO instead of MIMO, but at least the network will be operational. Now let's have a closer look at the specifications of our GPS synchronization device. It has an embedded GPS GLONASS receiver and an active antenna. It has 8 ports. One is used for the power supply and the other 7 for the connections with the radio devices. It is compatible only with the H08 devices, so with the MMXB, OMXB and QMXB base stations, and the Infilink 2x2 Pro family. It has the same ingress protection rating as the other Infinet outdoor units, and the power consumption is very low at 4 watts maximum. The choice of 7 sync ports for this device was made considering 6 sectors and a backhaul device. So, the time reference is obtained via GPS. The base station sectors are synchronized with each other using this reference signal. But if you have several base station sites in one city, then all of them will be synchronized thanks to GPS. The aux audio sync provides both intra-site and inter-site synchronization. Of course, you must have sync devices at each base station site. The transmission within the Infinet Wireless networks is controlled by the master units, so it is enough to synchronize them and the whole network will be in sync. There is no need to use synchronization devices for the subscribers. The connection between the aux audio sync and the Infinet radio units is done using a special cable called cab sync, which must be ordered separately. It can have various lengths depending on your requirements. To enable synchronization, all you have to do is go to the link settings section in the web GUI of each base station and check Use aux audio sync. Please remember that the frame length and the downlink uplink ratio must be fixed and identical for all base stations that need to be synchronized. Otherwise, the synchronization will not work. I have set 5 milliseconds and a 50-50 ratio, but this is just an example. You can set any values you require as long as they are the same on all sectors. Additionally, you can go to the system settings to enable GNSS position and GNSS time. This will allow the base station to use the precise time and coordinates provided by the GPS. The position of the unit can be displayed on Google Maps. The coordinates are updated in real time, which is useful when you have Infinet units installed on mobile objects. Okay, so far we've established that the GPS synchronization along with the TDMA firmware allows you to deploy a 4-sector site using just 2 frequency channels. But it is important to mention that in order for this system to work properly, your network must obey 2 very important rules. The first one is that a base station must not hear the subscribers from the opposite sector that uses the same frequency. This situation can occur when one or more subscribers are very close to the base station site at a few hundred meters, for example, and they have high gain antennas. If possible, the recommendation is to avoid installing CPEs with high gain antennas at close range directly in front of a base station. The second rule is that subscriber devices should not hear powerful signals from other sectors. When a subscriber is located at the border between 2 sectors, it will receive signals with similar power from both base stations. Even if the frequencies are different, since the guard interval is just 5 MHz, there could still be interference. A bigger guard might be required in this case. In practice, we are aware that this situation can be sometimes hard to avoid. In such cases, it is often difficult to find out exactly why your radio network is not operating at full capacity. Of course, our immediate recommendation is that you should contact our tech support team and they will be more than happy to help you debug the issues in your network. However, we're not going to make a big secret out of our optimization techniques. So in the next few slides, I will show you a few ways to solve some of the most common problems that can occur when these 2 rules are broken. So the first thing you need to do is check to see whether the synchronization works at all. To do this, go to the device status window of each sector and look at the sync indicator in the top right corner. If the synchronization is enabled and it works properly, the indicator will show the time since the last successful sync. In this case, the time is 0 microseconds, so the synchronization works fine. If the sync is lost, the indicator will become red, and if sync is not enabled, it will show sync off. Next, we must look at the list of subscribers connected to the base station. We analyze the main parameters starting with the RSSI level. Normally, it should be in the range of -60 to -40 dBm. Above -40, there is too much power, the receiver can be saturated or even damaged. Below -60, the maximum modulations are no longer available. And the reason for the low RSSI is most likely the poor antenna alignment or the presence of an obstacle between the base station and the CPE. Next, we look at the signal to noise ratio. Ideally, it should be above 28 dB, but you can live with values in the range of 20 to 27. If it's less than 20, then most probably the link will not work properly, because this parameter tells us how powerful the useful signal is compared to the noise level. In addition, we pay attention to the power imbalance between the RX and the TX. This can also give us information about some problems that can be solved by repositioning the devices. If the signal levels are good, but still the maximum bitrate cannot be achieved, or you notice a lot of retries, like more than 5%, then we can say with a good degree of confidence that there might be some interference problems, and most probably the sources of interference are your own devices. Now we need to find out which devices are affected and which devices are the sources of interference. To do this, we must go to the radio scanner tool in the device status window. This tool will show us the number of pulses per second detected by the radio, indicating the degree of interference. In the next slide, you can see that if the number of pulses per second is greater than 150, then the display lights up in red, telling you that the interference is very high. In addition, the tool will show you the MAC addresses of the interference sources if they can be decoded. Not only Infinet units will be listed, but other devices that use the 802.11 standard as well. If the interferers use different transmission standards, they will not be listed. You will just see the pulses. The letter N indicates whether the device is a node within the Mint network. If this sector knows about the device, its name will be displayed. If not, then the name column will be empty. Also, the signal level of the interference sources is shown here as well. If you conclude that the sources of interference are your own devices from other sectors, you need to somehow reduce their impact on the performance of the sector. The best way is to try and create a reflective screen between the back-to-back sectors to block the back lobes. Or you can consider installing the base stations on the side walls of a building if possible. In this case, the rear lobes will be completely suppressed. And you can also try to reduce or increase the height of your base station antenna so that the signal from the opposite sector is no longer captured by the back lobe. If these methods are not successful, you can try to reduce the output power of the subscriber devices. To do this, you can use the target RSSI parameter from the base station interface that automatically adjusts the transmit power of all subscriber devices. Or you can go to each of the problematic subscribers and reduce their power manually if you don't want the rule to be applied to all CPEs in the sector. Now let's consider the reverse situation when one of the subscriber devices has problems at the reception. It should be noted here that when you run a radio scan on a subscriber unit, you may not see the MAC address of the interferer. This is because the interfering signal is on the same frequency and it is perfectly synchronized with the useful signal. Therefore, at the moment when you perform the diagnostics, you may need to temporarily turn off the synchronization in order for the scanner to be able to decode the MAC address. Then you will know for sure who is the interference source. If the opposite sector is indeed causing the problem, again we have the same recommendations. First, you need to try and shield the opposite sectors from each other by inserting some kind of obstacle between the interferer and the affected subscriber. If this is not possible, you can reduce the power of the problematic base station, but only if you are ready to sacrifice a bit of bandwidth of the long-distance subscribers. You must gradually decrease the power of the opposite sector until the interference level at the subscriber's receiver drops below -85 dBm. In the end, I also want to mention that synchronization is recommended for point-to-point links as well if you use the same frequency for multiple collocated devices. So in any situation when your neighboring Infinet units might interfere with each other. So these are the main techniques that we use to diagnose and solve problems that might appear when implementing synchronization and frequency reuse. Hopefully, they will enable you to optimize your network and make your communication channels operate at maximum performance. Nevertheless, as I mentioned before, please feel free to contact our support team at any time for any issue. We will be more than happy to help you. Now, let's move on to the questions. About the synchronization device, does it work on all network at the same time or only for the current base station? So at each base station site, you must have one of these devices. If you want your whole network to be synchronized, each of your master units must be synchronized. So one synchronization device can offer synchronization for up to 7 devices on the same site. And if you want this site to work in sync with another site, let's say 1 kilometer away or 5 kilometers away, then the other site must have a sync device as well installed there. So this is how it works. Okay, next question. On one base station, some features like target RSSI are not available. Yeah, you must upgrade your firmware. If you don't have all the features, we always recommend upgrading to the latest firmware version. You can find all our firmwares on our FTP server. I can show you the link again. So in this slide, you have the link from where you can download the TDMA firmware. So if you don't have TDMA at all, or you have an older TDMA firmware, I recommend going to our FTP server and downloading the latest version, and then you will have all the features. Yeah, so as my colleague Bogdan said, most probably you don't have TDMA installed. If you have the default polling based firmware, you must upgrade it manually, so it's not automatic like with a regular firmware upgrade. There is a special procedure. We have a screencast on this subject. You can look it up on our YouTube channel. We have a screencast exactly on how to upgrade from Mint to TDMA. Next question about the beta firmware. This functionality is available only in beta firmware. If you are asking about the target RSSI, no, it's not only in the beta version, it's in the stable version as well. Next question. Different base stations can't be synchronized if they have same couple of frequencies. They can be synchronized, of course, but I have to ask you, you mean different sites or different units on the same site? Different sites. Okay, so if we are talking about different sites, you must have at least one synchronization device at each site. If you synchronize both sites, each site with its own GPS module, then both sites will work in sync, no problem. But the idea is that you must have a sync device at each site in order for the two sites to be synchronized with each other. Because yeah, the timing reference then will be the same for all units. Another question, why is not the GPS module is not integrated in the antennas of the base stations and subscribers? Yeah, so the R5000 devices were not developed with integrated GPS. In our lineup, we have the XG devices. Those have integrated GPS modules. They only need an external antenna, and you don't need a separate module that you have to power and so on. Another question, so we can reuse 4 frequencies in all network or 2 frequencies? Yes, it depends on how close are your base stations to each other. 2 frequencies for the whole network. If you have I don't know, tens or hundreds of base stations, it's hard to think that it would work. I would say that at least 4 frequencies you would need, as I showed you in the example with different polarizations. So 4 frequencies would be a bare minimum, but it really depends on how your network looks, on your setup. Very advanced radio planning design must be done in this case to see exactly how great the interference will be. So normally 2 frequencies will not be enough for the whole network. It will be enough for one site, for one 4-sector site, but if you have a neighbor site 1 kilometer away, let's say, working on the same 2 frequencies, then you might have problems. Another question, do we have these webinars available for later viewing? Yes, we will make all our webinars available on our IW Academy. You can go there and you will find all the past webinars, screencasts, and all other useful documents. It's easy to get there. In the Our Services section on our website at infinitewireless.com, you will find IW Academy. Next question, for TDMA, do we subscribe or apply for a license? No, it's not necessary to do this. The TDMA firmware is completely free. You just go to our FTP server and download it from there. It's not a separate license for TDMA. Next question, Infinet devices, can they work with an external GPS source that is not proprietary for Infinet? Unfortunately not. The R5000 devices have a proprietary port to which the GPS synchronization module connects. Okay, so another question about the omnidirectional antenna. This is an external antenna that we do not provide. We only provide units with integrated antennas, and the connectorized models are without any antennas, so you have to provide your own antennas for the connectorized models. Another question about synchronization. How is the synchronization done? Satellite database via satellite. So we have GPS GLONASS receiver that uses the satellites to get the timing reference. If you enable GNSS position and time in the system settings, then in the device status you will see the number of satellites as well that the device sees at a certain point. Another question, is it possible for an Infinet device to recognize another Infinet device that is not in the same mint area and without authentication? It depends on what you mean by recognize. So if you use the radio scanner, the Infinet unit, if it receives signal from another Infinet unit via the air, it will decode its MAC address, and you will see its MAC address there. So yeah, the answer is yes, it is possible for an Infinet device to recognize another Infinet unit in the area via the radio scanner. Even if they are not in the same mint area, they are not connected, it is possible for them to see each other. Another question, is it possible to upgrade devices from Mint to TDMA by installing TDMA to current Mint devices? Yes, of course. So you just take the file, the TDMA file from the FTP server, and just upload it on the Mint devices, and the firmware will be switched to TDMA. You'll get a message in the web interface that the new firmware version is different from the current one or something like that. You just have to click OK, and then you can install TDMA. But you have to do it manually. Another question, do we have to use the GPS module to get the use of TDMA upgrade? No. So you can upgrade to TDMA and get the benefits of TDMA without using synchronization. The synchronization is an extra only when you need to implement frequency reuse. But TDMA has some other advantages as well, like low jitter, and it eliminates the bad subscriber problem. Maybe we will cover this topic of TDMA in more detail in the future, but yeah, you can use it without the GPS synchronization module as well. So another question about the benefits of switching from Mint to TDMA. Yes, there is a list of benefits. You can find a document about this in our manual. As I said before, maybe we will cover it during a separate session in the future. But yeah, TDMA has some advantages compared to Mint, and Mint has some of its advantages as well, but it depends really on what you use the link for. And if you need very low jitter, for example, you can use TDMA, because by using the fixed time slots for each subscriber, the delay will be predictable. There will be virtually no jitter. And the bad subscriber problem, when you have a very distant subscriber that maybe operates on a low modulation, and it takes a very long time to transmit its data. With polling, all the other subscribers will wait for that bad subscriber to send all its data. But with TDMA, everyone has a fixed time slot, and it transmits whatever it can during that time slot. So all the subscribers don't have to wait for the slow one to transmit its data. The polling based firmware, the Mint firmware, on the other hand, has the advantage of a more efficient resource utilization in general. So the base station polls each subscriber to see what it has to transmit, and it allocates markers for the subscribers. Another question is in French. Can you please ask in English? Okay, the length of the GPS cable can affect the accuracy of the clock? No, I think not, because Our cables which we provide for our GPS synchronization module are designed to work with it. So I think the maximum length that we provide is 30 meters. We have tested cables up to 200 meters long, and there were no problems with clock accuracy. So if you really need to use more than 30 meters, I think you won't have any issues. Right, so there are no more questions, so it's time to end. Thank you all once again, and see you next time.